We have, to begin with, Hiroshi Ooguri, who is going to tell us about the ubiquity of metastable vacua.
Thank you very much. Can you hear me? Oh, no. Okay. Can you hear me? So, I'd like to join other speakers to thank the organizer again for having this conference in Madrid and for inviting me to give this talk. So, the ubiquity of metastable Dojita vacua in flux compactification of string theory is one of the central assumptions in the current study of landscape of string vacua. It has been argued that this assumption has significant implications on particle physics and cosmology. Therefore, in my view, I think this assumption deserves the closest scrutiny. Today, I will mainly talk about metastable vacuum in the context of field theory decoupled from gravity, but in a few instances, I will try to mention how things can change when you turn on gravity. So last year, interrogator Zyberg and Shi discovered that supersymmetric QCD with massive flavor has metastable vacua for certain range of flavor and rank of gauge group. And this raises various questions, such as how generic this phenomenon is in the context of field theory, and can this be useful to build a model beyond standard model, and can we realize it in string theory? Now, this is a question that I was initially interested in when I heard about this discovery, because so far, until last year, most of the exact results about string theory have been focused on things that are protected by supersymmetry, and this can be potential avenue where we can extend these exact results in case without supersymmetry. And indeed, we had very interesting talk by Shamit Katur in relation to that, and I imagine Kamal Baffa will tell you more about this later. And finally, the question is, how does the story change when gravity is turned on? So let me first discuss how generic the existence of metastable vacua can be. So I'm going to give you two classes field theory in which we can display metastable vacua. The first type was studied by myself with Yutaka Okochi, who is a postdoc at Caltech, and Park, who is my graduate student. And this is about class of n equal 1 gauge theory that you can obtain by starting from n equal 2 gauge theory and perturbing it by adding superpotential. So give me any n equal gauge theory that has Coulomb branch and pick almost a generic point on the Coulomb branch. For example, in the case of pure SU2 Zyberg-Witten theory, you have this massless monopole point and the massless dion point, and then give me any generic point P. Then I can find for you a superpotential W which generates a metastable vacua like that at the point P that you have asked me to do something. Okay? So in this particular example, the potential would go like that they are zero at these 2 points, and then it can be a metastable. The point P can be metastable. So how do I do that? Well, this actually follows from the simple fact that sectional curvature of Coulomb branch for any n equal 2 gauge theory has is positive semi-definite and generically positive definite. So let me explain how this works. So let's start the geodesic coordinate expansion of the metric in general. In Kähler manifold, you can have an expansion like that. And then let me just choose superpotential to be linear in this geodesic coordinate in such a way, and I choose this geodesic coordinate so that it vanishes at this point P. And K is some constant vector. Then you can see that this bosonic potential can be expanded in this way, and in particular, the positivity of sectional curvature just means that for arbitrary choice of this constant vector K, this matrix is positive definite, that they have positive definite eigenvalue. So that means that you have this confining potential around z equals 0. And this positivity is a simple consequence of the fact that metric can be written in this way, once you know that the metric can be written in this way, then you can show that the sectional curvature is positive definite. So this is a consequence of the rigid limit of special geometry. I should also mention that this geodesic coordinate may not be globally defined on Coulomb branch, but we can replace this geodesic coordinate z by finite order polynomial of vector multiplet field, and you can replace that at least for the purpose of stabilizing this point, and then that does the job. And in fact, we can say more about this. In the case of group SU2 or SU3, we can choose W to be a single trace operator, in fact, of finite order polynomial of vector multiplet field. And such deformation can be realized in string theory, for example, a la Cacciazzo, interrogator, and vacua. We have not been able to show this fact in the case of general SUN, not because I see any obstruction, but because the metric form of the metric is just complicated. But in particular point in modular space where the form of the metric simplifies, then we were able to show, even in the case of SUN group, that we can choose superpotential to be single trace operator of finite order polynomial of vector multiplet field. Another thing I want to point out is that this interesting fact that you can engineer metastable vacua at almost any point in modular space is the consequence of the fact that the sectional curvature is positive definite. In fact, you can easily, but equally easily prove that if the curvature is negative or zero, then the same potential V has no local minimum with positive energy for any choice of superpotential. So this is rather interesting because naive genericity argument might say that, well, if you allow me to choose any superpotential, then I should be able to engineer metastable point, a generic point in modular space. And then this fact clearly says that such a naive genericity argument fails. And in fact, this property relies heavily on the positivity of the sectional curvature. And in this context, it is actually interesting to point out that if we turn on gravity, the sectional curvature of vector multiplet in n equal to supergravity is not positive definite. And in fact, this was one of the features that distinguishes swampland from the landscape, as was pointed out in my paper last year with Cameron Buffer. Indeed, if you look at this potential that's appropriate for theory with finite Newton constant, then it was shown, which was pointed out by Dennis and Douglas a few years ago, that for flux compactification with one modulus, there are no metastable Dogita vacua in the large complex structure region. And it is interesting to note that in the case of one modulus, in fact, in the large complex modular structure region, the curvature indeed becomes negative. But it is actually surprising that they also found that there are no metastable Dogita vacua even in the conifold region where curvature turns positive, so one might naively have expected that based on similar argument as I have given here, that there could have been metastable vacua. Of course, this is a consequence of the difference of the form of the metric, but also of the form that the W is restricted to be of the form of Gukok-Witten buffer potential. I should point out that subsequently, Dennis and Douglas found that in the case of multi-moduli, in some limits of the modular space, one can actually construct a metastable Dogita vacua. But others have shown later that there are other regions in modular space where there are no metastable vacua. So clearly, I think that situation in field theory where you can do, it appears that the metastable vacua is rather ubiquitous. This situation seems to be rather different in the case with gravity, and I think this deserves further investigation. Now let me give you another class of field theory in which I can demonstrate existence of metastable vacua. So this is a work based on, this is a work in collaboration with Kawano, who is in Tokyo, and again with Okochi. And we found that any vector-like quiver gauge theory has metastable vacua. And to be precise, I mean that we consider any quiver gauge theory that has adjustable superpotential for adjoint fields and the masses for bifundamental fields that connect the nodes of the quiver diagram. And in some range of parameters, by that I mean that I can adjust masses of the bifundamental fields and also the rank of the gauge group. And in fact, again, many of these gauge theory have geometric realization. In string theory, started by Douglas and Moore, and then followed by many people. And again, the argument is quite simple. So suppose you give me quiver diagram that satisfies this property, and then we can pull out some sub-diagram gamma 1 connected to another diagram gamma 2 through a node like that, where you have bifundamental field here, connecting node 3 to one of the node here, and then again to another node here, and the adjoint field here. And this node, the quiver gauge theory associated to this sub-diagram, can be integrated Seiberg-Schie model or its variant that was investigated last year, and so that it has metastable vacua. And if the interaction through this node is sufficiently weak, then this metastable vacua will not be disturbed. But it is actually important that here we are, this is possible, this kind of argument is possible because we are allowing metastability. This kind of argument would not have worked if we are looking for models without supersymmetry vacua, since small perturbation like that can easily generate SUSY vacua. And in fact, the way that it is propagated, the supersymmetry breaking effect gets propagated to this other region is interesting. The way it happens is that if you have add mass to this adjoint field, then that generates this caustic interaction between this field and this field. Therefore, if the supersymmetry is broken here, like in the case of ISS, then that can feed in here and break supersymmetry through the standard gauge mediation process. And this way, the supersymmetry breaking effect in this sub-diagram can propagate through quiver diagram. And indeed, this idea was recently applied to study metastable vacua in AN time quiver gauge theory by Girardello and collaborators. And again, I have to give a couple of comments. So first of all, again, I want to stress the fact that in these two classes of models, in both of these cases, there are long-lived metastable vacua for some range of parameters. And this should be contrasted to the case with models without supersymmetric vacua, which seems to be non-generic. And there is a difference between inequality and equality, that in order to have this kind of feature, you just have to have certain inequality among parameters of the theory, whereas in order to engineer a theory like that, you have to have strict equality for parameters of the theory in general. And this comment is the same as what Ferdinando asked about during the talk of Shamit Kachru, that these field theory models have frozen parameters, and so when gravity is turned on, they become dynamical, so we should worry about stabilizing them in appropriate range. So the second question was that, well, is this useful for model building? And then if it is so, what kind of feature of this metastable vacua allow it to be useful? So I would like to just give you some example of how this can be useful. Basically, the point is that, again, as I said over here, that metastability requires inequality among parameters and not equality, and this simplifies model building. So in general, constructing models without supersymmetric vacua is hard, and this is because there are lots of constraints. For example, Whitney index, which you can compute in weak coupling, can give constraints on absence of SUSY vacua, and also there is a famous Nelson-Dieberg theorem on R symmetry. And realizing them in string theory is harder than something that I can tell from my experience. But many of these difficulties can be avoided by accepting metastability. So Whitney index or Nelson-Dieberg theorems are no more obstructions, because these are conditions for the absence of SUSY vacua, and so if you can live with SUSY vacua, then these are not obstructions. And also, it gives greater flexibility in choice of parameters. So for example, superpotential can be generic, and in particular, we can break R symmetry and generate gaugino masses at one loop. So with Kitano, who is a track, and Kochi again, we propose some model of direct mediation based on this concept. And direct mediation, I mean that the hidden sector which breaks supersymmetry carries standard model charges. So therefore, SUSY breaking effect is directly communicated to visible sector. And to use ISS model for hidden sector directly is difficult because ISS model has R symmetry, unbroken. So therefore, because of this, it's difficult to generate gaugeino mass at a level that's comparable with scalar mass as required by phenomenology. But given that we have greater flexibility, we asked ourselves, well, how about breaking our symmetry explicitly by superpotential? That's a simple idea. So, this is what we tried. So we start with SUN gauge group with NF flavors, and these are standard chiral fields. And the superpotential like that would have given you ISS model. So what we propose to do is just add photic potential, and of course then this will be non-renormalizable interaction. So you have to ask how this can be completed in ultraviolet, and I'll briefly mention that later. But the point is that adding this, of course, breaks R symmetry, so that's a desired property. And in fact, in our paper, we also gave a realization of this kind of model in terms of intersecting brain. But as I heard from Shavitz-Kachur, that this model can also be naturally realized on D-brane at Calabi-Yau singularity, because just like in the previous slide over here, integration over adjoint field typically generate quartic interactions like that. So this is an interesting class of model which has nice ultraviolet completion. And if you choose the mass matrix over here to have two eigenvalues like that, and then appropriate symmetry property for this cortex interaction, then you can arrange so that you have a global symmetry of the model like that. And in that case, the quark bilinear gets supersymmetry vacuum extraction value like that. And this vacuum is long-lived provided that we choose this mass to be sufficiently larger than this. This is the same condition that ISS model had, and with some appropriate choice of this quartic interaction. And so what direct mediation model should do is that hidden sector field should carry standard model charges. So we're going to say that this global symmetry actually is the gauge symmetry in the standard model sector, that it includes this SU3 cross SU2 cross U1 charge of the standard model. And the reason that we choose this and not this global symmetry to contain the standard model charge is because of the Landau pole issue that I'll mention later. So anyways, here. So it turns out that if we do all this, then the mass of gaugeino, scalars, and gravitino come out to be phenomenologically attractive values. And the Landau pole problem can be avoided. By that I mean the following. So if you have minimum supersymmetric standard model, then this four gauge coupling would converge to one value at the ground unification scale. But since we have this direct mediation model in which we have additional fields which are charged with respect to standard model charge symmetry, so when this field turns on, then the running gets changed. So then the worry, but the unification still happens because they come in the SU5 multiplet. But the worry is whether this goes to the negative value. And if that happens, phenomenologists call this as the Landau pole problem. And but we can avoid this problem by choosing these parameters in appropriate range. So this gives you sort of example of how we can use this idea of metastability to build an interesting model for phenomenology. And in fact, subsequently, there has been much of model building activity making use of related ideas. So actually, I'm afraid that I'm finishing a bit too early, so that I give you plenty of time for you to get on the bus. So metastability vacua appears to be ubiquitous in field theory, and accepting them allows greater flexibility in model building. And realizing them in string theory is easier, and I think that this is an area that should be and will be explored further and teach us a lot about non-supersymmetric aspects of string theory. And that's what I meant here, that it may lead to new technical advances in string theory, and we have lots to look forward to. And there are still outstanding questions. This is one of the questions I asked at the very beginning, which is still there. How does the story change when the gravity is turned on? And how can we tell when they are not in the swampland? So with that, I'd like to end. Thank you very much.
So thank you very much, Hiroshi, for keeping to time. Do we have any questions? Lando.
Sorry, you said this, but I missed it. Since you are using a non-renormalizable operator, I'm a little worried. What is the gravity no mass? Is it as high as the intermediate scale, or is it lower?
Let's see. So the thing was that, first of all, so in this case, I think that we chose the gauge. This would happen. Well, so let's see. So this C square, this quadratic coupling is actually given by this formula. And in order for this to work, I think we have to choose this gauge coupling scale to closer to the Guth scale. And in that case, I think that we can choose gravity no mass. I forgot the exact value, but at a reasonable value.
But it's lower than
right. So it's lower than these values. Lower than supersymmetric breaking point. Yes.
Thank you.
So that gravity mediation is subdominant. Yes, that is indeed true. That if you choose lambda to be closer to m-Guth scale than these other scales, then we can suppress the gravity mediation effect compared to direct mediation effect. Okay. So that you don't have to worry about forever changing neutral current and these related issues.
Thank you.
I should have mentioned that. Thank you.
We have any other questions? Yes.
Maybe you said that, and I missed. What's the scale that suppresses these high-dimension operators, either in your example before with n equals 2 or in the more phenomenological one?
Well, let's see. I think that in the intersecting brain picture, this was sort of given by relative angle of this brain. And I think that in our paper we argued that when this is small, there is an R symmetry. So there is an approximate R symmetry that makes this parameter relatively small.
When you try to do realistic model building with that, what scale did you have in mind?
Well, so as I said that I think M is of order in this range, and you have to choose lambda to be closer to m-Guth. So that means that C square is suppressed by, I think, the power of 10 to the minus 6 compared to m or something like that. Yes, compared to the scale set by m.
Any other questions? We have time for one if there is. If not, let's thank Hiroshi again. And we move on.